our next speaker is joining virtually. I hope everything works out there. But he's online, and that was a thumbs up. So yeah. So the next speaker is Ankur Handa. He's a research scientist at NVIDIA Robotics, where his work focuses on the intersection of perception control and machine learning for robotics. And prior to joining NVIDIA, Ankur completed his PhD at Imperial College, and he was a research scientist at OpenAI as well. His interests span a range of topics, including computer graphics for benchmark tracking and SLAM systems, as well as applying deep learning for scene understanding. And his more recent works explore leveraging GPU-accelerated physics and reinforcement learning to bridge the sim-to-real gap and vision-based teleoperation for performing complex robotic tasks. And with that, I hope you can share your screen.
Let's see.
Perfect. And can we maybe
put this all okay?
Yeah.
Let me know when I should begin.
Can we put this sound on the room speakers?
Can you hear me all okay?
Is that fine for you guys? Okay, yeah. Go ahead.
Okay, so my talk's going to be about exploring the frontiers of dexterous robot manipulation, but with simulation. So I think you can do a lot with simulations. I know there's been a lot of interest lately on collecting data with teleop systems. And I hope I can show you that you can do a lot with simulation also. So what is our mission here? Mission is to build a superhuman dexterity. So the superhuman part is extremely important here because we can't be limited by the human performance. And our focus is on high-value dexterity as characterized by the breadth of human utilization in manufacturing. So dexterity is working with your fingers to perform intricate, high-value manipulation as opposed to just grasping. And it requires arm and body coordination along with leg work if you're looking at humanoids for force transfer and navigation. But the key here is to really move the hands to the specific location with your legs and stuff, and then do the manipulation. And that's through leveraging the fingers to do that. I think I want to also highlight this talk that I saw a few months ago from David Silver, which was showing all the great things we have been able to do over the past few years by doing RL and self-play. And the key thing that is they're all superhuman. So while we can do a lot with supervised learning, but the recipe we have converged on as a community for more complex things happens to be RL and self-play, which is how we get superhuman performance. If you want to beat a human, you have to have some form of RL into it. So before I begin, I want to highlight some of the previous work we've done over the past 5 years. It started off with the Dex pilot work, which was when I was thinking about building teleop systems with hand and arm. At the time, it seemed like, well, we are going to have to do something beyond RL. And I started off building that with purely vision-based system, so you can move your hands around in a workspace with 4 cameras looking at it. You can track the hand and you can relay the motions over to the robot and it will do the teleop. And sort of figured out that it turned out to be far more complex than I thought, both the teleoperation system development and the teleoping, and then learning from those demonstrations. So I gave up on that and moved towards going back to doing sim-to-real. So I started off with Dextream, which is basically a system that does in-hand cube manipulation inspired by the OpenAI work, and the Dex-PBT work that followed afterwards, which was looking at hand and arm systems to do the reorientation. So the PBT stands for population-based training. And then we had follow-ups on Dextream FGP, fabrics guided policies, which impart smoothness and collision avoidance implicitly into the system. And just recently, we had this system that does hand-arm coordination to do the grasping of objects lying on the table. So that's basically the summary of all the at least my past 5 years of work. So I'm going to start with Dextream, which we developed in 2022. So I'm just going to play the video to show you what it does, and then walk you through different steps on how we built that system, and then move towards others. So the task of this is manipulation, job is to coordinate and orchestrate the fingers so that you can rotate the cube such that the orientation matches with the jump on the bottom right. So the whole idea is to just keep doing that in the loop until it drops the cube. This was, again, done using a combination of CoRL and you can see there are a lot of places where it seems like it needs to do some deliberate movement of the cube to achieve the orientation. And it does that very gingerly and very nicely to get to the target. This one's also pulling the thumb through to rotate the cube. And no real data was used here, no teleop, just to emphasize that a bit. And we had a cube pose that was tracked by a vision-based system. So this is also an interesting bit where it gets stuck and then figures out that it has to move the cube in a different direction. The thing recovery.
Ankur? Oh, can you just... We can't really hear you while the video is playing.
Oh, okay. Well,
maybe you need to sound.
Okay. So just to give you the history and motivation behind it, so that was the OpenAI system back in 2018, and it had all sorts of sensors on it and shadow hand, and to do the in-hand manipulation, and they were using phase space markers on the cube to track the orientation. They also had a vision-based system, which wasn't that great. So our motivation for this work was to simplify the hardware. We believe that you could do a better, build a better vision-based system and track it using a combination of deep learning and geometric computer vision. While this system that they developed with vision was just end-to-end, where they would regress from image to the corresponding pose directly. So we avoided that. And we also use GPU-based simulation as opposed to what they do in that work, which was Majoko-based. And we brought the time down from many months to just a few days. And I think one of the things I want to emphasize is both examples of how scaling up simulations for context-rich manipulation can allow sim-to-real transfer. So that was basically the message. This was done with Majoko, and we did that with Isaac Jim. But the underlying theme is very much the same. Can you use high-throughput simulation with the combination of domain randomization to do sim-to-real transfer for this context-rich manipulation task? And the answer is yes. So I think just to give you flavor of what it had, we had all sorts of state vectors that we used within the simulation, and we used RL with the combination of automatic domain randomization to scale up the system. So on the left, you see is the state vectors that go into the actor and the critic. So we had the asymmetric actor critic, so meaning that the actor would get the observations that it's going to get in the real world, and critic would also have far more than the actor and some privileged information that you cannot get in the real world. The neural network controller would take object pose, which we developed through computer vision and deep learning and geometric computer vision. It would take the history of joint angles and the target orientation, and it would provide you the joint targets. The key difference between the stuff OpenAI did and us is also the hand. If you have four-finger hands, they're much more difficult to control or learn from, as opposed to the five ones. There's a lot more movement and redundancy you have. So Allegro hand learns cube rotation slower compared to the shadow hand. But the input and the output is something that's displayed here, which is the object pose, join angles, target orientation, and you get joint targets. Pretty simple. So what is automatic domain randomization? So the key thing about here, the automatic part here is that every time you train with domain randomization, you can evaluate slightly outside the ranges of which it was trained on. And based on the performance, you can shift the ranges and retrain. So you do that for all the parameters you have, and it gives you automatic curriculum, and it's also giving you infinite data, all the data you can mine from simulations. With a classic domain randomization, your ranges are fixed. So you only get so much data, but if you adapt it based on the performance, meaning that if you're performing really well, you keep expanding. If you are not performing well in certain range, you shrink that range a little bit, optimize for another parameter, and come back to it. So simulations also give you a way to sort of evaluate in the loop. And the evaluation is extremely, extremely fast because you're doing that in simulation, as opposed to running experiments on the real robot, which happens to be much slower. So the transfer to the real, I think it's the highlight of that result was we reduced the training time from multiple months to 2.5 days. So this was what they had with OpenAI, and this is what we had with automatic domain randomization. We beat their vision-based and state-based XL results by a lot. They also had some results with XXL, which they ran it for multiple months. I think we could have done that as well, but at the end of the day, we saw that there's a significant gain we get by running a vision-based system alone. And the number of consecutive successes were capped to 50. Therefore, we provide these stats for 50. In our case, the max number of consecutive successes would go to about 100 or 150 at times. So that's the difference. So I'd like to show some of the other bits of the results here. This was another attempt.
Can you maybe try to mute the video?
Can you see that now? I think the deliberate movements that you see here are actually very interesting.
We still can't really hear you.
Can you hear me all okay now?
Yes.
Can you hear me all okay now? Okay. I guess you will miss the sound. Like, I think I'll stop it here. I also have the high frame rate video, which I think is very interesting. It does the which are really fun to watch. I love the thumb flicking through. We rotate the cube. It drops it as well, just to let you know that it's not perfect. The other one that I quite like is this one where you see the smoke coming out of it. And that happens all the time when you're running experiments on the robot. You're going to break the hardware at some point. I guess the message here is that no matter how many layers of robust software you add, you will always feel the hardware. So Allegro is still not as robust as many other robots, especially with shadow hand as well. So we did break it after working for it for a while, but in the subsequent work, I'll show how we can learn policies that are more gentle to the robot and we can get much more smooth trajectories out of it, because RL by the very nature learns bang bang control, and it's not very smooth. So the next work, I think, which I want to highlight, is the work where we add fabrics to the system. So geometric fabrics is the work that Nathan Ratliff and Carl Van Wyk developed. So we added that on the Dextream system to provide gentle and smooth behaviors that transferred really well to the real world also. And the difference is pretty obvious when you see there's the motion of the fingers, and there's also, when you do the FFT, you see the smoothness on that, which I'll show a bit later on that as well. So you see that train policies can be pretty hard on the physical hardware, and that's mostly because it's flopping the fingers and randomly moving, and you do exponential moving average to smooth out, but still the noise is still there in the behavior. So fabrics guided policies are supposed to be more gentle, and you can see the behavior as you in the video. It's far more robust and smooth, and this work was basically all about how we can develop systems that are gentle to the hardware, and they have baked in smoothness and collision avoidance. So your standard dynamics equation with a joint PD controller gives you the torque, and you can do that. So fabrics learns another additional layer of QF and QF dot, and basically the policy is omitting F by A, and A uses the fabrics layers that provides a smoothness, second order smoothness on the velocities and on the joint angles. And that's basically what this work is about. And we show that the fabrics guided policies are just as good as the Dextream based policies, but they tend to be really smooth. So I guess I can skip that here to show you the smoothness. So you can see that Dextream policies tend to have a lot more noise in them, as opposed to the Dextream FGP policies, where if you do the FFT, the behaviors, the frequencies and the amplitudes, they're pretty obvious here that the ones you learn by vanilla RL tend to be far more noisy. There's another experiment that I did on this where I was being very adversarial to the hand, and yet it did pretty well on that. So I think one other thing I would say is these kind of behaviors are very difficult to learn by, standard supervised learning. But with RL and in simulation, you can scale that up quite a bit, and this sort of robustness emerges out of it. So I'm being very adversarial to the hand here, and yet it's not losing the cube and not dropping it. Guess I should hurry up because I only have 12 minutes to go. I also want now, getting to the last part of the talk, is the pixels to action dexterous arm hand grasping with geometric fabric. So just to give you the flavor of what it does, the input is the depth image, and the action is basically the hold and the PCA space of the hand. Grasping, and it's able to pick up the object, quite reactive. A very funny grasp, but it did it. The other one I want to show is this, where it's following the key box, picking it up, and that's the other one that I highlight. Like a toy airplane. Again, everything is from pixels to actions. Sorry. So what is so unique about this work? It's the first time RL for manipulation on a 23 DOF system, 7 for the KUKA arm and 16 for the Allegro hand. So jaw-grippers-based robots often have the 7 DOF for arm and 1 DOF for the gripper. So this is 3x the complexity. Geometric fabrics is also fused in for inherent smoothness and collision avoidance. The other highlight is basically the end-to-end grasping via student-teacher distillation on depth images. We don't want to operate on point clouds. It's very reactive and fast and works on arbitrary set of objects. So the geometric fabrics has these design requirements which allow us to develop systems which avoid collisions. If you have different objects that you want to avoid in colliding with, you can turn them into boxes and bubble wrap the object with spheres so that you do sphere and box intersection. Self-collision avoidance, joint limiting, and the action space. Inductive biases as well, so I want to highlight that. We basically have palm pose for the full arms, so sort of an end effector in that sense. And then for hand, we actually learn from the data sets some PCA space for grasping, so it's tailor-made for grasping. Often you would find that if you do RL on high-def manipulation systems, it would just have fingers going around and just to pick up the object, but you don't want that. So you want something that is power grasp or precision grasp. So we can learn that from some of the data sets that are out there in computer vision. Redundancy resolution as well, and it's all vectorized. So the first step is basically learning from the teacher information. You have all the privileged information you can get in the simulation, and for we have different objects per robot. So you get object ID, which is sort of one hot vector, and then you learn with the classic asymmetric actor critic. You turn the handle, and eventually you will learn a policy that's able to pick up an object from the table. Now the second part is basically distilling that onto directly from depth image. So you have a student-teacher online dagger-based system, which is fairly standard at this point. And we also regress to the object position here so we can visualize. So you have an auxiliary head that's giving you the object position, and then an action space basically giving you the action trained all on using an online dagger system. And then comes the real world deployment. You have a state machine. Every time you pick up an object and drop it in the bin, you reinitialize it and go to the home position and redo that process. And on the bottom right, you see that we are able to also visualize and ROS the object position. So that helps in debugging as well. So, and you have picked up when you can read the depth or the height of the object position. Say you raise the object beyond a certain height. Now it's time to drop. This was the object set we trained on. About 140 BizDex objects. We have a lot of variety in them. We also had some scaling of the object masses and everything done to add more diversity. And this is now different behaviors that we show. And you can see that having auxiliary head that gives you the object position is actually very useful for debugging. We don't really use it for anything else other than debugging to make sure the network has learned something that we can visualize. Again, this exogenous disturbance handling is something we also did by network external four-stalk perturbations. So the speed control, you can also change the speed at which it's able to move and grasp an object by changing some parameters in the fabrics. So that's inherent, which is often very difficult to do with the standard RL policies. If you train it with an EMA of 0.9, it's not always possible that it would work with 0.5 if that's your way of slowing down by averaging. Here it's much slower, so you can see how slow it moves here, but without changing the performance significantly. Again, you're getting depth as an input. I didn't mention it here, but we also simulate noise, depth noise in the simulator when we do the student training. But that's pretty standard at this point, so I'm going to skip it. Generalization to soft objects. It wasn't trained on this, but yet because the behavior is all about power grasping, it's able to do reasonably well on soft objects as well. And this is the full video of set up by 8x. You can see it has these retry behaviors as well. And it's just one run, not many runs stitched together. Okay. So some parting thoughts here. Simulations are a path towards building high dexterous systems. Majority of the grasping systems today use simulators to train, especially the jaw grippers ones as well. And personal experience has been that getting tally operation data from more complicated manipulators is extremely non-trivial. The system I developed 5 years ago with the Handa tally operation, it was a lot harder to collect data, and perhaps there's a better way today, but I sort of was one of the reasons why I moved back to doing RL. So RL is a recipe for superhuman performance. Most superhuman systems today use RL in some form or the other, including the ChatGPT-based system. And BC is a special case of RL. Other thing we learned from the last system is that direct end-to-end dexterous systems that map pixels to actions are really robust. And I think it's basically the future, given the nature of diversity we're going to encounter in the real world. So with that, I will end my talk.
All right. Do we have questions in the room? Yeah, there's one.
I think I can't hear the question.
Oh yeah, I will repeat it. So the question was, what strategies are you going to use in the future to push this even further?
I think I mentioned about self-play and RL. I think one of the things that has been underexplored in robotics is self-play. There was an interesting paper from OpenAI in 2019, Alice Bob doing self-play to do the grasping and or goal reaching as well. So I think that's one thing that we would like to explore. As you may have seen with Alpha 0 and Mu 0, self-play was crucial. And I think that area is still underexplored in robotics, and that I think will require interesting work in simulation development and training as well. So that's one thing we'd like to explore. I think it's also possible that you're going to have to do, if you want to do some functional grasping, you're going to have to do deep mimic style stuff as well. And that's something we are also exploring, but not by collecting zillions of demos, because for anything to do with hand and arm, demo collection becomes very difficult. So these are the two areas I would highly recommend spending time on as well. I think we should learn a lot from the rise of alphas from DeepMind. Those things have been underexplored in robotics, and perhaps it's time to revisit them and apply those ideas here.
Okay, so then I also have one more question. We've seen a trend at CoRL that people are first pre-training on data and then using highly curated data sets to fine-tune. And with simulations, it feels like, especially with contacts, we're having a rough approximation of what contacts are in the physical world, but people oftentimes complain that they are not really accurate. So the question is kind of, is there value in having a high precision simulator, or do you think that just having enough randomization kind of deals with a problem without having to be too realistic?
I think there's certainly value for real world data. Oops, sorry, just gonna switch off. I think there's a value in real world data for pre-trained backbones, but I think if you want to do evaluation and scaling up, that will only come from simulation, even if the simulators are not super accurate. But I think we are going to be developing over time more accurate simulators. GPUs are going to get better and better over time, so you can simulate a lot better as well. But I think overall, the kind of robustness you get by training in simulation is very hard to get in the real world. And I could see basically BC and RL coming together, where possibly for distillation you can use a pre-trained backbone, but you have a lot of these skills that you're trained in simulation, and you're trying to do multi-teacher student compression. I think there's interesting work called MRM-D, if you haven't seen it, which is doing something along those lines and putting together VLMs as well on top. So I would also say LLMs are also looking at now synthetic data. So there's another axis to be explored. But I think there's a belief that you cannot scale simulation, because somebody has to create the environments, and you have to make sure that things are very stable, etc. But we can learn a lot from all the content creators who've done amazing work in graphics for about 30 years or so. And there's a huge amount of data we can explore from there. You know that today graphics is also learning from games and super sampling and stuff. So I suspect we will use some real world data, but I think a lot of data will come from simulation as well.
All right, then one last round of applause.
Thank you.
And thank you, Ankur.